Okay. Hi, good evening. Thank you very much for your presentation. It was really amazing. My name is Nima, and I think some of them knows me.
Hi, Nima.
It is my second PhD in civil engineering. My first PhD was based on the computer science, and I'm so happy to be here. And we are working on the how we can get the real number for the CO2 emission in the concrete. The funny things here is that we always talk about the concrete, and we said that 8% of the CO2 emission is for the concrete. But I don't know why nobody talk about this 7% of the CO2 emission is just because of the war that we have before the Ukraine and Russia. Before that, they created 7% of the CO2 emission, and if it was another country, it will be the force. And we are working on the CO2 emission on the concrete, and as you know, the concrete made by some material, okay? And all those materials has the specific number of the CO2 emission, okay? And if we want to calculate it, it is something like that, for example, X plus Y plus Z, and it is the CO2 emission number. My question is that when we talk about the CO2 emission, why we always say that we want to reduce the amount of the CO2 emission in the concrete? It's obvious that, for example, for this concrete, the amount of the CO2 based on all those material is this. What do you want to optimize? If you want to change the amount of the material, at the same time, we should look at the strengths. And in this case, it will be the multi-objective problems. Or sometimes it can be many objective problems. And we should focus on this problem, that how we solve this problem by some algorithms that we have. And my question is for the first presentation, when you say that it is optimization for the amount of the CO2 emission, please don't put us in a black box. We want to know that what's going on inside. Why we talk about the optimization. Why, what is the meaning of the optimization here? You want to change the number of the material or not? And the second concern is that for all those materials, as I read a lot of papers, a lot of books, by changing the materials, the amount of the CO2 emission a little bit will be changed. The most of them is based on the transportation, that we never talk about this. And this is another thing that if we see a lot of application, a lot of papers, they talk about the material, but nobody talk about the transportation. Transportation is the most and important part of the CO2 emission exactly for the concrete. Thank you very much. I appreciate it.
Nima, may I ask the state of affiliation?
University of Miami.
Okay, thank you.
Yeah, thank you.
Well, so I think maybe let me cover the different things that you said. The first thing is optimization is not a black box, and it's actually very simple. Is for concrete, 95% of the embodied CO2 is cement, right? So optimizing concrete, that means reducing cement. Like that's very simple. So the question is, how can you reduce cement without so you still need to achieve performance. You don't want to pay more, right? Typically, and so the only way to do that is to play with what you have, right? So you have supplementary cementitious material that you can replace cement with. Maybe you can switch to more expensive aggregates. Sometimes you switch to more expensive aggregates that allows you to reduce cement in return, and you can actually save money for that. Or you can use chemical additives, right? So you can use plasticizer, strength enhancer. So all of those things, it's using what we have already and using that to decrease the amount of cement in concrete. So it's not like a secret formula. It's really about minimizing cement. How much cement per cubic yard do you use in your concrete? The second thing is about the transport. I mean, the way we, we measure the carbon footprint of concrete, like there is some very clear methodology, like you build an EPD for concrete, you measure like the free contribution of the material, that's what you talked about, like that's the A1 contribution, like the footprint of the material that goes into concrete. Then there is the manufacturing itself, like that's the A3 contribution, like the plant, you need electricity for your plant, and then you have the A2, that's the transport that you're talking about, right? And I mean, at least as far as I'm aware, the transport is not like the biggest contribution. Like by far, the materials and the cement itself is the biggest contribution. So of course we can do some things to every reduction is going to help. So the reducing on the transport front is going to be helpful as well. But at least as far as I'm aware, it's really the cement that is responsible for 95% of the GWP.
Oh, thanks for the presentation, guys. I really enjoyed it. Danny Smill, Georgia Tech. So generally, we're talking about machine learning, AI. We're talking about making predictions within some sort of a space, right? And when you talk about a multi-dimensional space, it's kind of like, what the hell are we talking about? What space is this? But the question I want to ask you is, especially with civil engineering and structures and materials, what role will be extrapolation? What role will that have in AI? So thinking about machine creativity, can we make predictions outside of this data space that are either meaningful or can somehow contribute to whatever field you're working in? Thanks.
Each of you can add a little bit to that, maybe starting with that.
Oh.
Well, hi Daniel. I'm following you on ResearchGate, and I read a couple of your papers, so I'm happy to see you here. I think extrapolation, at least as far as I'm concerned, could be a little tricky, and I think what you're inferring is whether there's room for making some sort of AI that realizes something better for that regression problem, pretty much without the data, right? In my condition assessment area, I haven't seen it, but I mean, I'd be interested to know how does that really work, because with a lot of this AI, my impression is that you always need that annotated data set, right, with that unsupervised learning. So like you just throw random connections and see which one works better based on that annotated data set, or whether you're looking to infer some sort of feature yourself into it, which makes it maybe supervised learning. Yeah, so I guess I would love to chat more about that with you for sure.
I like the idea of AI-driven design in general. So I think being able to, make structures that meet the requirements and are very efficient in some dimension or some other was really compelling. But what I'm thinking is maybe the person to ask this to, the best person to ask this to would be the engineers of record. Because you're going to build something that looks really, really different. They have to sign off, and it might be good to just broker a discussion. Hey, if we really open up the limits here, the boundaries of the box, to what extent can we make you feel comfortable enough to say, here's the acceptance test, here's how we simulated it, and I will sign off on this?
Thank you. I think the question is interesting. I also think that if we would like to extrapolate something, we would have to think about, like, do we use this something that's outside our data set in our area in practice? And if we do, then there is going to be a need for extrapolation. But knowing what I know about what we have in civil engineering, most of our data sets are confined really because these are the mixes or the data that we use in buildings and bridges and stuff. Going outside of these may not turn practical unless it becomes maybe more cost effective. Then perhaps we can talk more about it, and I think it's interesting that you mentioned that. Thank you for your question.
Yeah, so what I would say is two things. So for extrapolation, of course, it's the most challenging, but that's also what we want, right? When it comes to mixed design, we don't want to discover something we already know, like we want something we don't. So I think that there is two things. First, when we extrapolate, we need to be aware of the uncertainty of our prediction. So I think that's something we have been working quite a bit, at least in my lab, is to come up with, whenever machine learning makes a prediction, it's one thing to make a prediction, but also to be aware of the uncertainty. And the further away you extrapolate from the training set, the higher the uncertainty becomes, right? So at least if you're aware of the uncertainty, then you know how far you can extrapolate before the uncertainty starts to deviate. And the second thing, I think on the long term, extrapolation is always going to be a challenge. I think the only way you can solve this is by having some physics-informed machine learning, right? So if you embed some physics or some chemistry, that's really how you can extrapolate and making sure you don't break the laws of physics and chemistry as you do so.
Hi. Thank you very much for your talks, everyone. They're really interesting. I'm Ollie from Converge, a company based in the UK. I guess my question is, well, I think I might have more than one, but I'll start with this addressed to Mathieu about, you spoke about your 1 million data points. It makes me think, I don't know if you've ever heard of the term survivorship bias, but the study they did in World War II where they had the airplanes that came back with all the bullet holes in, and they looked there to see, I don't know, to identify some pattern based on the data. It strikes me that in concrete data, if your data set is established from, decades worth of mixed designs and associated performance data there, you're likely to only have the successful mixed designs. There's unlikely to be records of mixed designs that didn't work, that perhaps within that parameter space yielded poor results. Have you got any thoughts about how to address that kind of survivorship bias in the data that's available today?
Yeah, no, I think that's a really good point. What I would say is that we'd be surprised that there is actually quite a few. Things don't always go wrong. Things don't always go right? So you have some examples, and whether it's doing a trial batch and miscalculating the water or using the wrong material. So we do some mistakes, and actually we can learn a lot from those mistakes, right? I fully agree with you. Like sometimes we learn more by a failed experiment than by a real one, and so I think there's two things that comes to mind. For me, the first thing is, as we share data, as we try to build new data sets, like you're absolutely right, we should not have any bias. We should include everything, including when it doesn't work, because that's how we can make sure the machine learning learns when it works, but also when it does not. So that's a great point. And I think, what you're also doing, right? Incorporating data from live sensors. That's how we can really make sure that we can collect as much information to the temperature evolution, role of relative humidity, all of those things. That's how we can understand when something doesn't work. The more data we have, the more we can understand why, and make sure that the machine learning algorithm also can figure out what was the pattern in the data that can explain why the strength was not as high as predicted. But yeah, fully agree with you. It's data, negative results, maybe even more important than positive results.
We automate this using adaptive experiments that I mentioned earlier. So you can bias the AI towards learning the space and sometimes making intentional mistakes to see how far it can push things in a certain dimension, so to speak, versus optimizing for specific KPIs. And I think, in a way, this is why concrete design is arguably difficult for humans to do, because it's very difficult for humans to have the discipline to, okay, I'm going to intentionally make mistakes just so that I can learn better about moving in the wrong direction, so to speak.
Robert Thomas, Clarkson University. So my question, it really deals with ethics and a little bit of risk and reliability. And I guess the question is, how do you decide what the acceptable level of accuracy is for a life safety application? So we're not talking flat work or anything, but certainly structural concrete life safety application. I know this is concrete, but let's say we're looking for fatigue cracks, life safety application, something super important. How do we make sure that our models are accurate enough that we're not missing things that are going to cause serious structural failures? And if that happens, how are we assigning risk and reliability when it's a computer that's at fault?
Maybe I can start. I think in my mind it's not so different from what we are already doing. You know, in the building code, we are building for, let's say, to have a failure probability of less than 1% or less than 0.1%. So we can do the same using a prediction with machine learning. If we can make a prediction but also have the level of confidence of the prediction, we can always, instead of predicting that the concrete will hit, let's say, 5,200 psi, we can say it's going to hit 5,800 psi plus minus 600 psi, something like that, right? So if we can have the full confidence interval of the prediction, which we can get that using machine learning, like using GPR or other types of machine learning ensemble. We can estimate the full confidence interval, and then we can design for a 1% failure. So in my mind, it's not going to fundamentally change the risk. And when it comes to liability, I think it's going to be pretty much the same as now. It's still a probabilistic issue. So I don't see it changing so much.
Thank you. I also agree. I mean, if you look at the equation in building code, it came up from like a few tests. Committee vote on it. It's there. We know it has like beta of 3 point something, and we're all good to go with it, right? So if we can follow the same approach with AI, whether AI comes about it a way that it just come up with it spits a number with the confidence interval, or it just shows you that this is the reliability given these conditions are met, then I think we also should be good to go. My biggest concern with AI is you can't really blame the AI for it. You're going to have to blame the user, because the user should be the one who actually goes on and signs on these things, not AI. AI is just a tool. It's like a very fancy equation to use, I guess.
What we're developing is not intended to skip any step in qualification and testing. Rather, it's to accelerate the discovery of better formulas that then enters the steps into qualification and testing and application, just like it does today.
I think that's a very interesting question. The way I look at it is that it's a technology, right? So just like you brought up a good example, fracture critical failures, right? Surprisingly, what they do with those components, like in aviation, they have this fracture critical analysis. So there's inputs that user need to input that information in based on what's happened in the past, what they feel about these technologies coming in, replacing hands-on manned inspections. So I could see it go through certain things like that if AI is ever implemented, because the way we do use AI now, it's based on experiments. And you can't really do that with reliability, right? As brought it up ironically. But another point of view, I think, my colleagues brought up, and I think it's been interesting that they even used AI with the justice system. And they found out that a lot of the times AI found the people who judges found guilty, that they weren't guilty, AI would have found them not guilty, just based on the certain amount of cases that they fit into a model. So I think it should be used as a calculator, a very advanced calculator, but certain things still need to come from human beings, and it's going to be their judgment.
Ryan Hankensifkin with Concrete AI. Mathieu, unfortunately, this question is not going to be for you. It's going to be for the gentleman at Meta. I think if you look at like some innovations in concrete, let's start with like a typical route of it going from academia to a concrete producer, and the contracts that are in place in a project, going from ready mix producer, concrete place and finish, general contractor, architect, engineer, owner. And here we have an owner that's kind of like bypassing all of those steps and going into concrete technology themselves. What things did Meta learn, and what are you doing to actually implement what you've learned into your building operations, in building new infrastructure, knowing that you have a net 2030 commitment to net zero?
Yeah, great question. To reducing our carbon footprint is important to us, and this is one of the levers. So let's talk about the levers that we're using here. One is design. So we're redesigning our data centers constantly to reduce the quantities of concrete that we want to use. Second one is reduce the carbon intensity of the material we have to use. So this fits into that. And then in addition to that, we also do insetting and so on and so forth. But, we're looking at the decarbonization effort really comprehensively. And this is one of the tools that we're using to get there. We would like the win to be that AI is used to help discover low carbon concrete quickly. And we think that being able to show that a building owner like Meta cares about doing this in a quantitative way is quite important. We've spoken to many construction companies and other building owners and concrete suppliers, and even to accept that this is a quantitative optimization problem, that's, to us, is already a win. Not everybody thinks that way, unfortunately. So that's how we see it. We don't intend to monetize it because we're Meta. We have no business here. We don't intend to grow a business here. But being able to reduce the barrier for the world to use low carbon concrete, then we get the win that we really want.
It's pretty hot. Hello. My name is Michael Hanna. I work for PS Engineers. It's a structure company. So we are the EOR. So I heard while you're answering the last question. First, thank you all for your presentations. They're really amazing. I'm really interested in AI, machine learning, and how we can use it in optimizing our design, like you mentioned. There is a lot of moving pieces in our design. One of them is concrete mix, but there is also concrete quantities, especially in footings and all of this. So what I'm thinking is there any research that you guys are working on to optimize this process or not? Thank you.
Well, for Meta, we're starting small, so to speak. We think that optimizing concrete design is a starting point. We don't have activities beyond that for the time being.
Maybe one thing is, so for now, at least the way we looked at it, and many people have looked at it, is optimizing per volume, right? So for 1 cubic yard of concrete, how can you decrease the carbon emission for that? But there is also the other way around, which is like if you can have a stronger concrete, maybe you can use a lower amount of concrete, like build thinner walls and that are able to carry the same weight, right? So those things can also be done. I think it's good to start by optimizing piece by piece and very clear optimization problems. But yeah, you're right. Like ultimately, we need to see that as an ensemble, including maybe taking into account like the thermal properties of the isolation from the concrete, how it's going to affect like cooling in the data centers, things like that. So I think it's good to start with like piece by piece, but yeah, at some point we need to put all of those pieces together to make sure we have the most optimal solution.
I think with mixed design, I teach reinforced concrete. I haven't looked into the AI application, but I'm sure there are great opportunities because 3 great minds are talking about it. And
you can go to GitHub and download ours.
Sure, if I ever have time, we'll do that.
Must be a professor.
Yeah, I just said that. So I always use conventional methods, right? The ACI tables and whatnot. And they seemed reasonable to me, but I could see the potentials there. But on the other hand, one thing that I would like to point out, I think there's already a place for optimization of your design and overall strength, and that's the structural reliability, right? You use distributions, standard deviations, 2-dimensional analysis, all sorts of chi-square, things like that, and you end up with these loss functions or strength functions, basically demand divided by or minus a strength minus demand, I think. Something along those lines. Anyways, yeah. Well, Mark taught it, so I thought maybe you know. So I think that's the best place for it, right? And now, one other thing that I would argue maybe we should be cautious with that is I look at a lot of our past failures in the United States, things that we didn't account for, like when we didn't know we need enough stirrups in our beams, and then an earthquake happened, and then we're like, ooh, we need stirrups, right? So when I look at it and I'm like, okay, if the material was not stronger than we designed for, what would be the level of catastrophe that would happen for that, our ignorance? Because structural engineers, our job is to model inaccurately material that we don't fully understand into simple geometrical forms that they're not really accurate, and just hide this flaw in a way that public doesn't know the amount of ignorance that goes into our profession. So that's all we do. There's a lot of uncertainty. So there's a reason this profession is as conservative as it is. It's built in, right? Because when something goes wrong, there's a lot at stake. So, but again, it's a great tool. AI is a great tool, and it would be not smart not to use it in any possible way that we can do.
Hi, my name is Bruce Smith and I work for the San Diego Association of Governments, and we do capital projects on the railway, mainline railway from LA to San Diego. And one of the things, and I'm also on ACI Committee 365, the Service Life Committee. So as well as using supplemental cementitious materials to extend the service life of our bridges, we are actively moving the goalpost. All the highway bridges in this country are typically designed for 75-year service life. So we're designing our railway bridges to last at least 100 years. So by increasing the design life of the structure, you get the biggest bang for your buck in terms of emissions, because you don't have to replace the structure for 100 years. So knowing the tech industries moves very rapidly, are you considering extending design life of your data centers? Is that part of your strategy to reduce emissions?
I assume you're speaking directly to me. Yes, so circularity is a really important lever, especially when it comes to hardware, which is another big source of a carbon footprint in data centers. So we're engaging with our suppliers on, for how long can we keep the servers running, and then if we have to retire them, can we reuse parts of it? So, for example, like the racks that contain the servers, surprisingly has very high carbon content. They're made from aluminum, there's a lot of copper in them and so on. And so if we can recycle them, they would be great. If we can reuse them, even better, because then the cycle of virtue, it's shorter and they become more efficient. So great question. We're not quite there yet. Facebook is not old enough to have reached end of life in any of our buildings.
Hi, thank you for the presentation. My name is Luis Hernandez. I am professional engineer in Canada. My question is regarding the comparison between the different materials in buildings, let's say concrete, steel, wood, etc. Even adobe or some traditional materials, let's say. Is there any application in the AI for doing this comparison fast or
like the
quick
environmental effect of them, or?
No, I mean, let's say like one of these buildings, is it more efficient?
But in what way?
In the carbon,
environmentally.
Carbon reduction?
Yeah. Well, I'm sorry to jump in here, but I think USDA has a website that, based on the material type and the square footage of your building, you can kind of get the, what do they call it, CO2 impact number or something like that. So, but it's a very rough LCA, simple life cycle analysis. I don't think it's very detailed.
Yeah, I mean, I think so. Some of the information is there. I think we probably need better methodology to really accurately calculate the carbon footprint over the entire service life of the structure. What I would say is that concrete, since we're talking about this, is actually not bad, at least on a per mass basis. If you compare with steel, for example, steel is much worse on a per mass basis. So for concrete, it's really the scale. Of course, we are worse than wood, but it's really how much concrete we make that is the problem, not so much concrete as an individual material. But yeah, I think to your point, to have really a good comparison, we need some better full LCA analysis of those different materials.
Hi, thank you for your presentation. My name is Ali Hassani. I'm from University of North Dakota, a master's student. I have a question. You mentioned that we are using AI to mitigate or eliminate the human bias, but we are teaching the AI, so it's inherently biased.
Is it for me? I think the word human bias was in my slide, so I'm going to start. That's on me. So I was specifically talking about impact echo data, and with that, there was a human bias on, or chain dragging where there's a human bias, right? When different people hear different echoes, they might mark that under or subsurface defect in different ways, right? Now, with the AI, it's not the AI that exactly saves us there. It's AI infused with the controlled laboratory data collected that from the locations we knew where the exact subsurface defects were at. And that's what I was trying to convey with the consequent slide was, even though we got very promising result with the lab data, the same model, same methodology when applied in a real field, it did not produce the same results because, yeah, there was no ground truth. And in that manner, it wouldn't help with the human bias. But if you're talking about a specific type of data, yes, it would help with the human bias. You could give that data to 10 different inspectors using the conventional methodology, and they come up with 10 different ratings for that same region. But AI, as there was case examples with the different mixed design and using different building codes, it could do a better job when you know the structure of your data, I would argue, but I'll leave it to you guys to go ahead.
I think this is more for you.
Come on, you're meta, you do everything.
We try to do as little as possible, actually.
I think your answer is great, and I mean your question is great, and I also think if you start to think about what could go wrong because we taught AI or like we designed AI, the effects will always be there, I think, but the magnitude or the impact would be problem dependent. So, for instance, say you have a problem, whether you have large data sets or small data sets, depending on many things, you could see much more effects of human bias or designer bias or coder even bias, provision bias in certain things versus other things. So overall, I think it's always going to be there, just like having a caudal equation for shear strength of concrete. This was voted because a number of committee members voted on it. The bias is inherently there, right? 5 years from now, they're going to change it because you have different information, which could be like new tests or new committee members or new something else. So this is a philosophical question, which I always appreciate, but I think the answer is going to be difficult to figure out exactly how to address it across multiple problems, I guess. I hope this helps a little bit. Thank you.
Yeah, maybe. So, yeah, regarding the bias, I think maybe it's actually good that there is some human bias. At least I think we are not fully ready yet to fully trust AI with everything. So at least maybe we should not call it bias, but we can call it intuition. Like, so the fact that it's not just AI predicting something, but it's a human being helped by AI to do his job faster, but still using its own intuition to say, I don't trust the AI here, or I think this mix is not going to work. Or so I think it's important to keep this intuition and to keep the human in the loop. So I think that's the first point. The second thing is, I mean, you're right. We teach AI. I would go one step further. We don't simply teach AI. We are, as human, have created AI, right? So we have created those algorithms, and we have created them kind of mimicking, like for example, the artificial neural network. It's an attempt to mimic how the brain works, right? So I think there is always going to be this bias that we are trying to replicate how we would approach things. So you're right. Like there's probably going to be some kind of human bias in the way the AI thinks. There is also the interpretability issue, right? Like when we want to understand what AI is predicting, like if I ask a quality control person to explain to me why he thinks this mixed design works, like I cannot just open his brain and see how it works, right? He's going to explain and provide some kind of interpretation of how he came up to this conclusion, right? But so I think the way we approach AI and the way we can try to understand what AI predicts is always going to be through the human angle, and maybe that's not a bad thing. Maybe it's good to keep this human in the loop.
Thank you all.
Sorry, I'm not here. I'm Satoshi Fujimoto from Tsunami University, Japan. I have a question regarding how, you mentioned that you use machine learning as a tool. And for example, if you use a mixed design, we ordinarily specify how we design the mix of concrete. For example, in Japan, maybe I use this recommendation for mixed design, and also this or something. I think in US maybe we did the mixed design in accordance with ACI something, and that is something that we use the tool to specify how we design something. And my question is, if you use your software, how do you specify the tools? I don't want the question that I use this software, and how do you actually specify? The software is just a name, so it has to be specified by in my opinion, it has to be specified by algorithm or the settings, or even all the models that we used. And that is something what we say, we use this recommendation because you open up the book, you have the equation, so everyone knows what you use as a mixed design. And for the software, how do you specify what we used as a tool?
Maybe I can start, and I'm sure you can have more to say. But at least for us, AI does not replace the specification, right? So AI is going to replace the intuition or the need for multiple trial and error. But at the end, AI is going to prescribe a mixed design. But you still need to test it. You still need to make sure the strength is high enough and to follow the same certification that you would use already, right? So I think the certificate AI that is, or at least for now, maybe one day we can directly trust AI and we don't even need to do the trial batch. But at least for now, we are not there yet. For now, AI can help you converge faster to the optimal mixed design, but it doesn't replace the actual trial batch, right? So I think that's the first thing. The second thing is more like, what do we include in those specifications? Like, so at least in the US, you have like everything that is very pure performance based. So where you only say, I want my concrete to have this strength, this slump, this shrinkage, etc. So pure performance. And then it's up to the AI to find what's the most optimal mix design that's going to meet all of those performance. And so that's typically how we can get the most carbon savings. And then you have like more like the prescriptive mix design, where the certification directly tells you you have to use 25% fly ash replacement, you have to use this water to cementitious ratio, etc. And in that case, there is very little room that we can do with AI, because everything is already kind of frozen, right? So what I would say is that the more we move towards performance-based rather than specification-based, the more we can benefit from that. But at least at the end of the day, it won't replace the trial batch and using the same kind of certification that we already have.
I think it's important to maybe delineate the process here. You know, like in my mind, there are two parts. Let's talk about the second part first. For a given concrete formula that you would like to use, let's say the supplier and the construction company, then they have to test that formula, you know, using break tests and so on, eventually bring it to the EOR, such as you, and then look at it together and agree to implement it, and then you move on the next steps towards construction. And then the first part is how do you come up with a formula that you like, and that's what the work that we're doing is about, accelerating that process. But when you reduce it down to a mix, to a formula, then it should be just like any formula that you would subject to the same steps and tests and deliberation you would for concrete.
Well, maybe my example was not right, but if you think of a FEM, a finite element method, if you use the software, you have you have to specify which model, how you cut the meshes or something. And I understand what your explanation, but I believe that doesn't mean that you don't specify anything in your design. And my question was how you specify. You know, I use the concrete.ai and that's all, or.
I think, if I may, I think the FEM is there to predict performance, and that prediction is the deliverable from that effort.
And AI is also used in that domain, I believe.
I cannot speak to it because I don't work on FEM and AI, but in my mind, the AI for concrete mix design, the strength curve from that effort is not the deliverable. It's the formula that is then tested, and the output of the C150s is the deliverable.
Let me just share my 2 cents. Maybe it might help, it might not. I've seen a study very, very recently. You know matrices, right? So if you have 2 matrices and you multiply them, there is a very specific way to multiply matrices. I think Google Mind, what they did, they just collected massive number of matrices and they throw it to their own generic AI. And their AI was able to find a new way to multiply matrices that's 30% faster than the way that everybody was taught how to multiply matrices. So coming back to your question is, there are ways where you can potentially create some form of AI that would be able to figure out a specification or at least understand the data structure to come up with a procedure or a way to predict something given what it knows about the structure. Now, as my colleague has mentioned, you could also infuse maybe some physics modeling, some physics infused, some chemistry infused stuff into the mind of the AI to make it a little bit faster in realizing, well, because of all these physical, chemical law I have and this data, I can find a new way to arrive at this output. Now, this could be something very passive where AI does the specification. You could also make it very, very simple, where you would say to AI, specifications to AI means if statements, if conditions. Knowing A given B, then find C. You could give it if statements, and hence this become your specification, and you would be able to figure out a way to come up with a prediction. I don't know if this would help with answering your question, but
I might add something too, since we are all doing our best. I think you're still not convinced, so that's why I'm saying we're doing our best. I think I think what we design in a lot of these AI methodologies are hyperparameters, and that's something that we design. And in the case of the supervised learning, you're basically optimizing a loss function. Basically the answer you're supposed to be getting versus the one the model gives you and the variation of it. So all you're doing is to make sure that function gets as small as possible, so it gets to 0. So it's a lot of optimization like that. And with CNNs, I believe it's a backpropagation. So all these connections, all these neurons we talked about are connected linearly, that has a slope and a point of interception, and those numbers are assigned randomly. They're connected together. Eventually they lead to a fully connected layer that has a probability. And that probability now, you can change that probability by backpropagation, by changing those A, B, and W's, weights we call them, or neurons. So those are the parameters we give it if it's purely AI, right? I guess you kept saying, what do you input in your system to make it happen? I guess as far as I know, we do use hyperparameter optimization. Learning rate is another one. How fast you want your optimization to change. Do you want it to go really fast or slow? So those are the things we play with sometimes to make the models work better.
Maybe one thing is, like, if you're talking about design at the structural level, or like designing the structure itself, I think what the AI can do is to remove the trial and error phase. So, like, for example, let's say you have a model, like a FEM model or something, and you say, okay, I'm going to test this structure and see if it seems like it's working or not. And then you say, okay, but what if this structure was slightly different? Does it still work or not, right? And so you can, if you're doing it like this, you can try thousands of different design and test it using your model and see if that works or not. So that's why I think we're trying to address with AI. We're trying to directly guide you towards what we think is the most optimal design. And then after that, you can still use the model that you trust to make sure this design is going to work. But it's the AI does not replace the model, doesn't replace the certification stage. It just replaces how fast do you get to the most optimal answer. How many can we reduce the number of iterations before we get to the final answer?
I think since we're just a few minutes away from the end of the session, maybe we'll give each speaker an opportunity to have some last words. Maybe you can tell us, where are we going? How close are we? And at what point are the AIs going to take over and go out and start designing concrete mixtures and doing condition assessment without supervision?
I just make a comment on the last one you asked. I think we shouldn't be worried about AI taking over all jobs, but it will, as autonomy has in the past, will take over certain jobs, and but it would create new jobs too, right? For instance, an example of it is that in our state, North Dakota, I was surprised to see the truck driver community, how they are promoting autonomous driving. They were because you still need human supervision, right? And they go through certain training, and it doubles their salary too. But there's going to be some layoffs, of course. So with that, I think AI has this role to improve our life for sure. But I'm not worried about taking over like crazy, because whenever AI model had the similar intelligence of a dog, then I would start being a little worried about it, right? My models are very dumb. The models I design are like, you change something, you're like, whew, all over the place. So I'm not worried about them yet. But you should worry about this guy. His boss is going to take over.
Well, let me compliment the community first by saying that there's a lot of innovation in concrete, materials, how we do things, how we build things, and that's all amazing. And to me, that speaks to the importance of AI because eventually you need to operationalize these innovations. They need to become concrete formulas that can be tested, that have the promise that you want, that you can optimize simultaneously, quantitatively, and get approval from the EOR. So I think AI can help in this, and I'm excited to be here with you. Thank you.
In my case, I'm much simpler than my two colleagues. I would say I think we would be wasting a lot of our time if we start AI from scratch. I think we might be better off looking at other industries like mechanical engineers, automations, NASA, how they discover galaxies and learn from them and start from there, rather than starting like from scratch from now, black box models and so on and so forth. And then 15, 20 years from now, we're going to realize, well, all what the last 20 years, we're just reinventing something that's already been done. So my advice is it's always cool to apply AI in our industry. Unfortunately, we remain appliers. Many of our cases, we apply AI. We don't really create new algorithms. We don't create new methodologies. I think if we complement that with our knowledge, we can make our own things for our civil engineering, and it becomes much faster and easier to use, I guess. Thank you.
Yeah, regarding the first thing of if are we going to lose our job for AI, I think there's a quote, but I'm just going to pretend it's from me, but I forgot who said that. But basically the idea is that scientists are not going to be replaced by AI, but scientists who don't use AI will be replaced by scientists who use AI. So I think that's the idea, that as long as we can follow this wave, then AI will allow us to do more, but hopefully won't replace us. So I think that's the first thing. The second thing regarding the time scale, I think that's actually the strength of what AI can do is that it can work with multiple time scales, right? So AI can tell you, okay, what's the best we can do right now? And, we can trial batch, and in 28 days, we can start reducing CO2 emissions right now. But AI can also tell you, okay, in 10 years, once you have all those new materials, new types of cement, new process, maybe completely new manufacturing method, like how do you optimize this, right? So AI will be able to, as new solutions and new materials become available, to still make sure we are as optimal as possible and accelerate that. So I think that's the good thing about those AI approaches, that you can use it and have an impact right now and start to decrease this depth that we are accumulating. But it's also going to remain relevant 10 years, 20 years as we get those new technologies available.
Any final questions?
Okay. Thank you all for the information. I have a very quick and specific question. So you guys mentioned you use AI to improve mix design, to learn crack. So especially for mix design, we know there are many content in it. For example, cement, sand rock, and fly ash, so on. And I'm just wondering how many ingredients are there in your mix design? So we know that maybe there are some newer ingredients which has less data points to input into the AI model. So how many ingredients are there in your mix design?
That's a great point. I mean, I think whenever you have new materials or new metrics you want to track, then there is some relearning that needs to be done. That's why we're lucky we're able to use our prior work on adaptive experimentation exactly to do this. When you have new materials, then okay, some of the dimensions are fixed, but you need to learn a new dimension, so to speak. Then we need to minimize the number of trials and errors. And that's why I think, all the innovation that are helping with sustainability eventually can benefit from AI accelerating the discovery of it, the discovery of the properties of it.
Yeah, so at least from our side, we work with whatever is available at a plant. So typically in a concrete plant, you will have maybe some silos for maybe 2 types of sand, 2 types of coarse aggregates, maybe also some pea gravel, you typically have one cement, maybe you have one fly ash, one slag, and you have a couple of chemical additives. So that's the scale we have been working on. What I would say is that what we call new material really depends on our definition of new. What I mean by that is that at the end of the day, even if we have some new cementitious materials, it's still the same underlying chemistry or the same underlying physics, right? So if we describe material not just based on their brand name, but more in terms of how the underlying chemistry of the material or how the fineness, or like how the physical and the chemical characteristics of the material are governing concrete properties, then so like for example, if we have a new fly ash coming in, it's not new, right? It's still an aluminosilicate material, right? So as long as we can predict performance not based on material by material, but more in terms of their underlying chemical and physical characteristics, then there is very few very new material in the concrete world.
Got it. Thank you.
I think in just the time we're taking at the end, we'll ask one final question. All of you can just give a 30-second input on that. So we know this year has been kind of phenomenal for AI with general public knowing about the LLMs and so on. In the next few years, things are probably going to go at exponential scale. How do you all think the things you are trying to achieve? What can, if the ACI community is also then convinced that they're going to use AI for concrete, what they can help you with, what they can provide you, that you can achieve your goals in the next few years? Your call for asking the audience in the room, if you could do this or help this or go in this direction, your goal could be achieved with strategy.
I'm going to respond within the application of AI in my domain. I think we have very clear understanding of what needs to be done in infrastructural condition assessment, and it's just a matter of how much the society and the owners of these infrastructure, both users and owner, want to keep them safe, right? So it's gonna be, if it's gonna be implemented, development, it's a different animal, right? But if you want to get it to see it implemented all over, you need to have that comprehensive support behind it. The other thing with the mixed design, I think, going back to the first takeaway I had in my presentation, I would say, tell me the specific needs you have, right? I don't really know what exactly is the target, right? There's no goal to use AI. It's just, let's use it. We get all these different applications. What's the comprehensive? And I think with the CO2 reduction, that was the first time we saw everyone's working in the same direction. But that might not be the only target ACI is focused on. So what are the other targets that they have as a community?
I think it would be great if we all work together to promote sustainability as something to optimize for. Because I feel like when we step out of this room, especially, people think sustainability is a sticker. You put some magic dust and then you get a sticker and then you win. Yeah, you're done. I think it would be great if we all talk about GWPs and CO2 per cubic yard, CO2 per structure, CO2 per function. I think that would be great. And then we can work together to use AI to make more sustainable data centers that can run more sustainable AI. That would be amazing. Thank you.
In my case, let's say two things. One of the greatest things that makes LLMs the advances in LLMs very, very quick and famous is because computer scientists, they share everything online. They don't really have to wait for journal publications. They just share it over Twitter and GitHub, and everybody has access to it. So it makes advances very quick. The other thing I would hope that ACI hopefully listen to us is education. Many of us trying to use AI now we haven't learned programming in our schools. We're graduated, we're already practitioners, engineers, right? So having a big educational component that makes educating AI or learning AI much easier would be very helpful for all of us, because then we would be able to figure out a lot of solutions that would, for our problems, I guess. Thank you.
Yeah, so I think in my mind, what can be done is addressing the main bottlenecks that are slowing down adoption. And I think at least in my mind, there are maybe two main bottlenecks. One is everything related to data. So making data available. I mean, I'm not sure if we can ever reach that, but at least even for a producer, like they don't always understand the value of their data and of maintaining them and making sure they can be used, right? So making sure that there is a culture in companies to maintain and make sure data can be discoverable and organized, curated in a certain way that it's going to be usable for them. Maybe not outside their organization, but at least usable for themselves. So I think that's the first thing. And then the second thing, at least in my mind, it's really the inertia. I mean, you can argue that maybe having inertia in the construction world is good. Like we want to be safe, but still, like inertia is preventing adopting those new technologies. And I mean, of course, now everybody is talking about ChatGPT and things like that. So there is a big PR, but I'm not sure if the perception of AI is really improving. Like ChatGPT can be extremely stupid sometimes, and if that's not really helping us in convincing industry that you can trust our AI model when ChatGPT can very convincingly and very proudly tell you that Earth is flat or something like that, right? So hope I'm not offending any flat society member here. But yeah, so I think in my mind, trying to convince people that AI there's nothing to be scared of. I think there's a lot of people who are also maybe a little bit defensive, that they don't want their expertise to be replaced by AI, making sure that everybody understands that AI is here to help you, not to replace your own expertise. I think that's one of the many ways we can try to overcome this big inertia in our field.
Right, with that, we are almost at time, so let's give a big hand to all our speakers.